Hello students, we are talking about Unit 3 of NCERT discussion, and this is classification of elements and periodicity in properties. We are talking essentially about periodic table. Periodic table is a very interesting chapter. Why? Because it is the first chapter which brings a lot of systemization and organization to an utter chaos. There are so many elements. There are 92 elements generally found in nature. And each of these elements forms thousands and hundreds of thousands of compounds, and these compounds, if they have to be studied properly, we need to arrange them a little more systematically so that we are able to study the properties more easily. And this organization is actually brought about by periodic table. Let's begin. This is a session of NCERT discussion. What is the basic theme of organization in the periodic table? How exactly is the periodic table organized, and what is the need for it? What is the theme? And the answer is very simple. There are so many different elements having different types of properties. Could there be a systematic method by which, if we arrange them in rows or columns, in periods or in groups, when we do that, then we find that either the properties are same, for example, in a group, or the properties show a very regular variation and a gradual change, especially if we move across a period. And this systematic organization, it makes the study of various elements a lot simpler. This is the basic theme of periodic table. Trying to arrange the elements in a sequence in such a way that their properties can be related, correlated to each other. Trends and similarities can be seen so that repetition can be avoided and they can be studied together more concisely. This, my dears, is the theme which is also answered here. I'm moving apart so that you can actually take a screenshot and use it for a verbatim answer in case you desire one. Which important property did Mendeleev use to classify the elements in his periodic table? And did he stick to that? There are two questions. Which property did Mendeleev use? Mendeleev used a property called the atomic mass number or the atomic mass. He said properties of elements are periodic functions of their atomic masses. He arranged the elements in the order of increasing atomic mass, and he found that properties show a very gradual variation as well as a repetition after a certain gap or a certain period, and that is why the term periodic properties. First part was this, and the answer is atomic mass. The second, did he stick to that? He mostly did stick to that, but there were cases when he made adjustments, like while moving from cobalt to nickel. As per the atomic masses which were available at that point of time, cobalt should have been more massive as compared to nickel. That was the estimate of the scientists at that time. Very boldly, based upon their chemical characteristics, Mendeleev proposed or suggested that this is not the correct location. He switched the locations of cobalt and nickel. He placed cobalt before and nickel later to make sure that the periodic properties match. So that shows that Mendeleev did suggest an important property or a rule, but the most essential portion of the guiding principle was the theme, that regular variation in the properties, and that is a must when it talks about the arrangement of elements in periodic table. What is the basic difference in approach between Mendeleev's periodic law and modern periodic law? The periodic laws state that properties of elements are periodic functions of their atomic masses. If you talk about Mendeleev, this has been the stand of Mendeleev. He talks about atomic mass. And the modern periodic law talks about the atomic number. And indeed, this was the case. Atomic number was found to be a more fundamental property as compared to atomic mass, and this is the major difference between these two approaches. one of the very big advantages was that all the isotopes, because isotopes have same number of electrons, they just differ in number of neutrons, right? So, since electrons are the ones which are responsible for chemical reactions, chemical bonding, etc., and if electrons are arranged exactly in the same fashion in isotopes, you find that chemical properties of isotopes are very similar. So they should be in the same group or in the same location of periodic table. If you take atomic mass as the fundamental property, you would place isotopes into different boxes or different locations. While if you're using modern periodic law and atomic number as the most fundamental property, you would find all the isotopes would be present exactly at the same location, which also reflects that they indeed have similar chemical properties. So yes, it's a big advantage for modern periodic law. On the basis of quantum numbers, justify the sixth period of periodic table should have 32 elements. If we just look at the organization of periodic table, my dears, tell me how exactly is the periodic table built? Well, you could derive periodic table from order of filling atomic orbitals, Aubau's principle. What? Yeah, we can. How exactly? Let me remind you of the trick. You have 1s, 2s, 2p, 3s, etc., etc. I mean, it can just go on. I'm just trying to write it down for you so that you can discover this on your own. This was the increasing order of energy, right? So once I have 6s, then I have 4f, 5d and 6p. So 6s, 4f, 5d and 6p. And at the end of P block, if you remember, you get a noble gas and the same period ends. So it begins with 6s, it ends with 6p. Each s orbital contains how many? 2 electrons. F contains 14, D contains 10 and P contains 6 electrons. If I add this number, I get 32 electrons. So, beginning from 6s and ending in 6p, I possibly can add 32 extra electrons. That means nucleus also can contain 32 more protons. Every time, the increments being in the units of 1 each. Like if I have 1 electron, then 2 electron, 3 electron extra. That means within the nucleus, 1 proton, 2 proton, 3 protons extra. That way, I could have 32 different choices. That means 32 elements can be present in the 6th period of periodic table, because the period of a periodic table is denoted by the principal quantum number of beginning and ending subshells, which is 6s and 6p. In terms of period and group, where would you locate the element with Z equals 114? Now this is very interesting. Here, I would appeal to you, please remember a few atomic numbers. Like, noble gases are very useful. Helium is 2, neon is 10, argon is 18, then krypton is 36, 2 plus 8, plus 8, plus 18, plus 18, then xenon is 54, and radon plus 32, that makes it 86. These are the classical noble gases. So we have radon, the 6th period noble gas, coming to atomic number 86. So if we have atomic number more than 86, that means we are moving beyond 6th period. And how many of them can be accommodated in the 7th period? 32 more. So 86 plus 32, that would make 118. So 118 would be the next noble gas. My atomic number, the given atomic number is only 114, which is less than 118. It means that it is not beyond 7th period, this is very well within 7th period. So, 7th period. This is fixed. One more thing. 118 is the next noble gas. Group 18, 118. Oh wow, this looks pretty cool. Yes. If group 18 is 118, group 17, 16, 15, 14 would be 114. Can you see this is falling so closely? So 114 would be group 14, 115 group 15, 116 group 16, 117 group 17, 118 group 18 noble gas. Oh my God. So what do we have here? It is simple, it is beautiful. What do we have? It's simply group 14, group 14 and 7th period. This is how we locate the group and the period in the periodic table. Write the atomic number of the element present in the 3rd period and 17th group. Now group 17 and 3rd period. I always encourage you, remember the noble gases. 3rd period noble gas is argon. Argon has atomic number 18. If argon is atomic number 18, one before that is chlorine with atomic number 17. And see, this is so funny. Group number 18, atomic number 18. Group number 17, atomic number 17. Group number 16, atomic number 16. So it just goes on right from, well, it goes on right for 3rd period completely. 3rd period begins with sodium and calcium. Although their atomic numbers are 11, 12, but the group numbers are very nicely 1 and 2. The moment you take aluminium, atomic number 13, group number 13. From aluminium till argon, you find that the group number is same apparently as their atomic number. It is chlorine we're talking about here. Which element do you think would have been named by Lawrence Berkeley Laboratory and Seaborg's group? The name itself reveals it all. Lawrence Berkeley Laboratory, lawrencium. Lawrencium, atomic number 103. Lawrencium, they started calling it, and seaborgium, and that is atomic number 106. They simply named it after themselves. That's it. Why do elements in the same group have similar physical and chemical properties? Well, it's quite clean. See, the thing is, if the elements are present in the same group, that means that they have same valence shell configuration. If they have same valence shell configuration, that means their chemical reactivity is quite similar. Why? Because say if they have one extra electron, that means all of them will release one extra electron. That means all of them would tend to behave as monopositive metals. Their valencies would be same. Their tendencies to either give electrons or take electrons or form covalent bonds would be quite similar. Since electronic configuration is the core or the central property which decides the chemical behavior, and within a group, since electronic configuration is similar, you find chemical properties are very similar. Not just this, since within a group chemical properties are similar, very often the nature of bonding and atomicity also is similar. Say for example, if you're talking about halogens, in halogens, if you have F2, Cl2, Br2, I2, all of them are diatomic molecules. In noble gases, all of them are monoatomic molecules. That is why, since the atomicity or the structure of molecules, all these natures are similar, you find that physical properties also tend to be reasonably similar in case we're moving down the group. So all the similarity in physical and chemical properties largely are dependent on same valence shell electronic configuration, and this is the key. to all similarity. What does atomic and ionic radius really mean to you? This sounds a bit interesting. They're asking about the meaning of atomic radius and ionic radius. How do you decide the radius of a circle? You start measuring from the center and you go outwards till the boundary. Now, in the same fashion, when we draw an atom, we should be able to say that this is the radius, right? But there's only one problem. And what is that? And that is that an electron doesn't have an exact location. It's a kind of cloud. Now, you can't really determine the radius of a ball of cotton or radius of a cloud because, I mean, whatever the reading you maintain or you obtain, it would just depend upon how hard you press or compress. So, ideally, you really cannot talk about the distance from center till the outermost point because there is no fixed outermost point when it comes to electrons or electron cloud. Then how do we measure atomic or ionic radii? Well, the simplest way is this. Within an atom, the only thing you can figure out is the position of nucleus. Experimentally, there is no way, absolutely no way to determine the location of electrons. Theoretically also that seems not to be possible. So what do? When we talk about atomic radius, say we want to find out the radius of an atom A. The first thing we check is, does this atom A form bonds like AA? Can it form a diatomic molecule like this? If it can, then what do? I would simply measure the radius or the distance from one nucleus to the other. And this distance D, I would divide into two halves like this. And I'll say D by 2 is equal to covalent radius. Please note, I can locate the distance between the nuclei because nuclei are heavy, solid, the location is measurable. I just detect the distance divided by 2 and I obtain a covalent radius. Very obviously, this portion is common. What does that mean? It very clearly means that I am recording something which is a little lesser than the actual possible radius. Why? Because for actual radius, I should have had circles or spheres just touching each other, right? This should have been the case. If they're overlapping, then naturally the distance D is a little reduced. So this covalent radius which I'm obtaining is expected to be somewhat lesser than the actual imaginary radius. But then there is no way I am aware or I can measure that so-called imaginary actual radius. So I just have to be happy with covalent radius. It sounds like we have solved the problem, but there is again a problem. And what is that? The problem is that not every element forms covalent bonds. So, say you have titanium. Now, titanium with titanium or sodium with sodium or magnesium with magnesium, they would form metallic bonds. Oh wow. Then what do? In that case, and since out of 4 blocks in periodic table, 3 blocks refer to metals only, S block, P block and D block, S block, D block and F block. All of them contain metals except hydrogen, of course. So there has to be some other thing also. And what is that? People devise something which is also called as metallic radius. What is metallic radius? The problem is, not all atoms form covalent bonds and not all atoms are metals either. So for non-metals, covalent radius serves pretty well. For metals, you take a metal in solid state, fine, and you determine the shortest distance between 2 nuclei. The shortest distance between 2 nuclei in solid state. And this distance dm by 2, you say, is metallic radius. So if you halve the distance between two nuclei in a covalent bond or a covalently bonded molecule, then you say this is covalent radius. Of course, both these atoms have to be the same. Similarly, if you have the distance between two nuclei in a solid metal, the nearest distance, then you say that is the metallic radius of that element in solid state. In solid state, the moment you're saying, it means that we're imagining that it could be different in different media, but yes, nonetheless. So you have covalent radius and you have metallic radius. Are they the same? No. Metals like sodium have also been found to make covalent bonds. So if you measure covalent radius in sodium and if you measure metallic radius in sodium, you would discover that they are different. But nonetheless, since there is no other way out, absolutely, we just are left with these two methods, metallic radius and covalent radius. And before we sign off, there is one more problem. What? There are atoms which form absolutely no bonds at all, like noble gases. How do we measure their radii? And for them, the idea is just cool them down. Now, I'm not angry. No, I'm not saying you're angry. Just cool the gases down, make them into liquids and finally solids. Take a piece of solid argon, for example. Just like solid metals, if you have a solid piece of argon, a krypton or xenon, try measuring the shortest distance between the two nuclei of noble gases in solid state. Which force actually attracts the molecules of noble gases? Van der Waals forces, right? So in that case, I hope you appreciate that there may not be any overlap at all. It is just that the molecules would be at a certain distance from each other in solid state as per the crystal structure. And this shortest distance between them, you take that shortest distance, whatever it comes out to be, and this distance by 2. This will give you a radius which is called as Van der Waals radius. So we have covalent radius, we have metallic radius, and we also have the so-called Van der Waals radius. Why? Because this is something which is measured between species which are not connected to each other by any solid metallic or any chemical bond, but which are just held together by Van der Waals forces. I hope this is very obvious that this distance is going to be a little more than the actual radius. Why? Because obviously they're not touching because of electrostatic repulsions, they're a little far away. They are a little far away, and hence this radius is going to be, I mean, if you're just measuring this, d by 2 would be this distance. This is a little more than radius, right? Whatever. But whatever that comes out to be, since, I mean, we can't measure absolutely anything else, we simply say that this is Van der Waals radius. There are 3 ways to measure atomic radius. Either you can measure Van der Waals radius, or you can measure metallic radius, or you can measure covalent radius, and the fun part is that often it is not possible to measure all 3 radii for a single atom, for every atom. So for some atoms, you just have metallic radius. For others, you just have covalent radius. For a few, you have both metallic and covalent. For some, you may have Van der Waals, and so on and so forth. This, my dears, is the story of atomic radius, and this is something which we say atomic radius means to us. Is there a possible relation or the order of covalent, ionic or metallic radius, or not ionic, covalent, metallic and Van der Waals radius? Yes. In a covalent bond, attraction is really strong. They're held, the shared electron cloud is in between 2 atoms, attraction is strong, and that is why covalent radius is always less, because atoms are much closer together. So you find that covalent, the radius covalent radius is always less than metallic radius. Why? See, overall attraction in metals is good, but if you just compare 2 atoms, they just let the electrons get away and they are delocalized in the entire mass. So it's great, but then overall, if you just say the attraction between 2 atoms, that is not as much. So you find they're a little far away and metallic radius is more than covalent, and obviously biggest is Van der Waals radius. So CMV, I hope you can see, It is just alphabetical order, and that also is the order of, incidentally, the order of increasing atomic radii. Covalent radius less than metallic and metallic less than van der Waals. So much so for atomic radius. All this I have spoken about atomic radius. What does ionic radius mean to us? Well, ionic radius would mean either the radius of cation or the radius of anion. Now that is another story altogether. So let's take a look at ionic radius as well. Whenever an atom gains any electron, gain of electron would mean, yes, what would that mean? Gain of electron would mean, well, that it is an anion now, right? If you have more electrons, if you are gaining more electrons, obviously the size will increase. And if you are removing electron, the size will decrease. Makes sense. So you would find that radius of anion is always greater than radius of a given atom, and atom is always bigger than radius of its cation. If I have Na plus or Na minus, Na plus is bound to be smaller than Na atom, and Na minus is bound to be bigger than Na atom, obviously. So if any atom forms a cation, it would become smaller, and if it forms anion, it would definitely become bigger in radius. Yes. What is the radius of ion, and what does this radius indicate? From nucleus till the outermost point, the distance would be termed as the radius. Yes. How do I determine the radius of ions? Well, that's not difficult. Say, for example, you take solid NaCl. If you take solid NaCl and you measure the distance between Na plus and Cl minus, this is radius of cation plus radius of anion. You can experimentally measure this in NaCl. The smallest distance between Na plus and Cl minus, that you could say is the sum of radii of sodium cation and chloride ion. So, radius of sodium and radius of chloride you can experimentally determine. But then you will say, but I don't really have individual values of Na plus and Cl minus. Okay, that's fine. We could actually try more. Why? Just see, instead of this, we could also determine radius of Na plus and Br minus together. Yeah, we can. I mean, these are the values I can experimentally measure. Then I could get potassium chloride also. And I could get potassium bromide also. What are you trying to do? See, sodium, potassium, chloride and bromide are 4 variables, A, B, C, D. And I have 4 equations in 4 variables, and these equations, the right hand side can be determined experimentally. Yes. If I solve them simultaneously, I would get the radius of each of these ions, right? This is how experimentally I determine the radii of various cations and anions using their ionic salts. That's it. How does atomic radius vary in a period and in a group? Okay. How do you explain the variation? That's not difficult to see. As I move across a period from left to right, nuclear charge increases. Nuclear charge increases. And electrons are added to the same shell. So, a shell represents the distance from nucleus. Now, if electrons are being added to the same shell, and the same shell is being attracted more strongly, very naturally, if you attract it more, atom would become smaller. So, we say that atomic radius goes on decreasing. Yes, indeed. So, we find, therefore, atomic radius decreases from left to right across a period. In shortcut, I could just denote it like this. Atomic radius decreases. This is across the period, this is down the group. What happens down the group? Let's figure that out. Down the groups, extra shells are added. Since more and more shells are added, that means it's something like you're constructing ground floor, first floor, second floor, third floor. So height of building will increase or the radius of atom will increase. You can say down the group, more number of shells, therefore bigger size. More number of shells, bigger size. So down the group, atomic radius increases, and across the period, atomic radius decreases. This is the periodic trend along with the reason. What do you understand by isoelectronic species? If different species have same total number of electrons, please note, total number of electrons present in species 1, if it is equal to total number of electrons present in species 2, then those species are termed as isoelectronic. Name a species that will be isoelectronic with the following atoms or ions. Fine. We have F minus, we have argon, we have magnesium ions, and we have rubidium cation. I am offered to discover the species, at least one species which is isoelectronic with these. Well, can I figure that out? Yes. Fluorine by itself has 9 protons in the nucleus and 9 electrons in the orbit. F minus means 1 extra electron, that means 10 electrons. So I have to find atoms or ions or species which have 10 electrons. Exactly. They would be isoelectronic with F minus. Which of them have 10 electrons? Well, neon or sodium or magnesium or aluminium ions. All of these would have 10 electrons and all of these are isoelectronic with F minus. Otherwise, I could take oxide ion or nitride ion. Each of them have 10 electrons. I was asked to suggest one species. I have suggested 1, 2, 3, 4, 5, 6. Take any one, and all of them are very much isoelectronic with F minus. In third option, I also have magnesium ions. So please note that incidentally, magnesium ions also have exactly the same answer. All the remaining species are also isoelectronic with magnesium. So F minus and magnesium, since they themselves are isoelectronic, you would find that their answers would be the same. Right? In this series, all these are isoelectronic species. Excellent. What about argon? Argon has atomic number 18. Now, by a similar logic, I could take potassium or calcium or scandium, even titanium for that matter. Oh my God. Each of them has 18 electrons. Yes, each of them has indeed 18 electrons. Or you could just take Cl minus or sulfide, even phosphide. And if you are too finicky, take silicide. Oh damn it, these species exist. Yes, they actually exist. And each of them, my dears, is isoelectronic with argon. You wanted 1, I have given you 8. All these are isoelectronic with Cl minus. Sorry, argon. Magnesium is already done here. And the last is rubidium. Now, rubidium, if you care to note, it happens to be just after krypton, atomic number 37. It is isoelectronic with krypton, yes. And incidentally, Br minus, well, very much. Or selenide, yeah. Or arsenide, love it or hate it, but yes. Go on the other side. You have strontium cation, very much. So, I mean, if you consider each of them, this is, just a moment, this is 36, this is 35, this is 34, this is atomic number 33. All of them are happily, sweetly, lovingly isoelectronic. Even yttrium 3 plus. Are they isoelectronic with rubidium? Yes. You could take any one of them and each of them is going to be the correct answer. Consider the following species. Oh my God. What is common in them? We just took a look. Well, nitride, oxide, fluoride, sodium, magnesium, aluminium, all of them have 10 electrons each. They are isoelectronic. We just see nitride ion. This is 7 protons in the nucleus. That means 7 plus 3, 10 electrons. Oxide, fluoride. This is 8 plus 2, 10 electrons. 9 plus 1, 10 electrons. There is no neon, but had we had neon, that also would have had 10 electrons. If you take a look at sodium ion, atomic number of sodium is 11. That means it has 11 protons and 11 electrons. And out of which, if you take 1 electron, it would be left with 10. If you take away 1 electron, that is by plus 1 charge. So, just see this. Magnesium, aluminium, same beautiful story. So what is common in them? They are all isoelectronic. They have total number of electrons the same. Arrange them in the increasing order of ionic radii. Now this is very interesting. Why? If they have same number of electrons, if they have same electronic configuration, greater the nuclear charge, smaller is the radius. Yes, greater the nuclear charge, smaller is the radius. So you find radius of nitride would be the biggest, then oxide, then fluoride. As the charge on nucleus increases, and how do we discover the charge on nucleus? This has only 7, 8, 9 protons, 11, 12, 13. Number of protons in the nucleus is going on increasing, and that makes the ion smaller. Indeed. This is the ionic radius order. Explain why cations are smaller and anions are larger in radii than their parent atoms. This is not a very difficult idea. See, cation is formed by removal of electrons from atom. If I remove electrons, maybe one, maybe more, do you see that electrons also repel each other? And their repulsion keeps the ball puffed up or the size of atom big. If I remove an electron, that means they don't repel each other as much. And if they don't repel each other as much, then the nucleus is always attracting them. If repulsion forces becomes less, you find that the force of attraction due to nucleus pulls them inwards, and thereby it decreases the atomic radius or the ionic radius. I have read another explanation. It says that now once we have lesser number of electrons, nuclear pull increases. Why? They experience, nuclear pull increases because now the nucleus has to pull less number of electrons, so it pulls stronger. This is a very loose explanation and scientifically it's wrong. So a more accurate way of saying is nucleus is attracting by the same attraction only, but because of removal of electrons, the repulsion between the electrons decreases. They don't repel each other, and once they were repelling each other, they were keeping the atom, big. Once one of them goes out, repulsion decreases. Nucleus is anyway attracting them. They are sucked in, and that is why the radius decreases. That is the correct explanation. Yes, for cations. What about anions? Opposite of the same thing. Mutatis mutandis. What? See, if we add one or more electrons, then repulsion between electrons themselves in the electron cloud increases. Yes. If they repel more, they try to go away from each other. And if they try to go away from each other, the size of spherical electronic ball or the atom increases. Due to greater repulsion between electrons, the size of an ion increases. This is addition of electrons. This is greater repulsion between electrons. This implies size increase, because if they're repelling, they go away from each other, which is possible when the atom gets bigger or the ion becomes bigger. That's why cations are smaller and anions are bigger than neutral atoms. 14th is a very valuable theoretical question. It says, what is the significance of the terms isolated gaseous atom and ground state while defining ionization enthalpy and electron gain enthalpy? And there is some hint also given, which is whatever. First of all, what is ionization energy? It is the minimum energy required to remove the most loosely bound electron from an isolated gaseous atom in its ground state to form an isolated gaseous ion in its ground state. So this energy is called ionization energy. Now they are saying, what is the significance of the term isolated gaseous atom? See, the thing is very simple. Instead of gaseous, had I had something like Na solid, giving me Na plus solid plus electron, this would have been photoelectric work function. Why? Light falls from solid metal, electrons are ejected, you get ions. What is this? This is clean photoelectric work function, nothing else. Oh my God. So, this is not ionization energy. As a matter of fact, if you want to convert Na plus gas, Na gas to Na plus gas, and if you just want to see the difference, watch this. Na solid to Na gas. I'm trying to judge if these differences are the same. They're not same. This is delta H sublimation of sodium, and this is delta H, minus of delta H sublimation of Na plus. This is sublimation, this is condensation or deposition, whatever. I hope you can see that tendency of sodium atom to undergo sublimation may be very different from the tendency of sodium ions to undergo sublimation. Yes. Since these two energies are not the same, I'm going and coming back, and since this difference is not zero, do you see that photoelectric work function is like from here, if I want to go here, this is the delta H, this is the energy change, and this would be equal to delta H sublimation of sodium plus ionization energy minus delta H sublimation of Na plus. This is very dangerous, because since this is not zero, I find that both these entities, photoelectric work function and ionization energy, could very well be different. And yes, dears, indeed they are quite different. So when they say isolated gaseous atom, is the word gaseous necessary? Very necessary. Why isolated? If it is not isolated, say for example, if I have Na2 gas giving me Na plus gas plus electron. Now in this case, during ionization, I am also supposed to break Na-Na bond. That is another additional nuisance, that is extra energy. So I'll keep on getting different values. So unless I have isolated gaseous atom, I will not get a unique number. If I want a unique absolute number which is experimentally reproducible, I have to be accurate. So when I say isolated That means, only one atom you have, and gaseous, and ground state also. Why ground state? Because if sodium already is in excited state. Say for example, to take electron out of sodium, I need 2 electron volts. Say for example, if sodium atom becomes excited and it already is excited by say 1 electron volts of energy, I just have to supply extra 1 electron volt to take out that electron, right? That is not fair, because most of the atoms do not stay in excited state. So I have to take this also. This has to be in ground state. As a matter of fact, this also has to be in ground state. Unless I clearly define their energy levels, I cannot measure the difference between the energy levels, and the difference between the energy levels is nothing but the ionization energy of sodium. So for accurately defining ionization energy, I must know that both reactant and product must be in ground state. Of course, they must be isolated and gaseous, and this, my dear, is the very significant portion of the definition of ionization energy. And very similarly, electron gain enthalpy also. Whenever you are measuring any energy changes, if you are measuring a change between 2 points, then 2 points have to be correctly, accurately defined. And for that, isolated, gaseous, ground state are very important terms. Energy of an electron in ground state of hydrogen atom is minus 2.18 into 10 minus 18 joules. Oh my God. Now, that means that if I have a hydrogen atom, it just has 1 electron and it has certain energy. Now, if I have to ionize this, that means I must move this electron away, right? And I must take it to infinity. And in this condition, energy of this electron is 0, because it is not interacting with the atom. From 0 till minus 2.18 into 10 raised to minus 18 joules. Please note, from this point I have to raise the energy to 0. That means extra energy I am supposed to supply is, which is 2.18 into 10 raised to minus 18 joules. If I supply this much energy, electron will jump from first orbit to infinity. That means it gets ionized. That means this is nothing but the ionization energy. Yes, this is nothing but the ionization energy. Okay. And this is the ionization energy in joules per atom. One atom needs so much. And I am asked, calculate the ionization enthalpy of atomic hydrogen in joules per mole. Joules per mole, yes. How would I get that? Well, instead of 1 atom, you take 1 moles. That means you just multiply it by Avogadro's number. So, ionization energy would be 2.18 into 10 raised to minus 18 joules per mole per atom into 6.023 into 10 raised to 23 atoms. And what do I get? I just multiply and I get what I get. तो ये आ जाएगा 13.13 into 10 raised to 4 joules per mole. Oh wow, quite a bit. Yes, indeed, it would be quite a bit. I mean, you could shift the decimal if you choose, but joules per mole was expected, and joules per mole is what we have given. It's roughly 131.3 kilojoules per mole otherwise. Among the second period elements, the actual ionization enthalpies are in the order. Dang to dang. Explain why. Beryllium has higher delta H ionization than boron, etc., etc. Now, this is an order of ionization energy when we move across the period in second period. Okay, and first let us graphically draw this, and let's also explore why is this the order, because that exactly is the question. First part is this, and the second part says why is it that oxygen has it lower than nitrogen as well as fluorine. Let's take a look. I think this has to do with electronic configurations. First of all, you have to appreciate that on moving across the period from left to right, size decreases. As size decreases and nuclear charge increases, attraction because of nucleus is increasing across the period, so ionization energy is expected to increase because you are pulling away the electron against the electrostatic attraction. So if there are more number of protons in the nucleus, they are attracting more strongly, so it is very much expected that ionization energy should increase, and it does. But does it increase very regularly? No. There are slight differences, like this is the trend. Let me draw this for you. If you take lithium, fine, and beryllium goes up. Interestingly, boron doesn't go up, it comes down. But please remember, when it comes down, it does not fall below lithium, it is slightly lesser. And then you find you have carbon. Okay. Then after carbon, you have nitrogen. After carbon, you have nitrogen. Very good. And then oxygen comes down. How strange. Slightly, not much. And then you have fluorine, which is very high. And of course, neon is a noble gas, so it just goes mad. Very, very high. This is typically the graph for ionization energy. And I have been asked to explain these two dips. Why a dip at boron and why a dip at oxygen. Actually, if you look carefully, you can relate this with their electronic configuration. Beryllium, now this is, lithium is 2s1, 2s2, this is 2s2, 2p1. So beryllium has higher delta H ionization than boron. Why? It is because in case of beryllium, the electrons are being removed. The electron is being removed from S subshell. S subshell is closer to the nucleus, and the electron in S subshell is held more tightly. It's attracted more strongly by the nucleus as compared to the p electron, which is going to be removed in the case of boron. Wow. S for strength. So since in the case of beryllium, 2s electron is being removed, which is more difficult, and in case of boron, 2p electron is being removed, which is easier. You find that ionization energy of boron slightly dips, and it is lesser than that of beryllium slightly. This was the explanation which was expected here. And then we have the next question also. O is lesser than nitrogen and fluorine. Why is it? See, across the period, ionization energy anyway increases because of increase in nuclear charge. So fluorine was very much expected to be more anyways. We are worried about why oxygen has lower delta H ionization than nitrogen and fluorine. How do we explain that? That can be explained by the extra stability of half-filled p orbitals. What? Yes. Nitrogen has electronic configuration 2s2, 2p3, while oxygen has electronic configuration 2s2, 2p4. Now, as nitrogen undergoes oxidation, what you can say is ionization, like this. Then 2s2, 2p3, you are removing an electron from 2p orbital, and you're just putting it like this. Half-filled p orbitals have extra stability, and ionization of nitrogen means you are destroying the extra stability of half-filled p orbitals, and that is why they need an energy which is slightly more than the regular energy they would be expected to need. Okay, and in case you're looking at oxygen, opposite is true. Why? Oxygen has electronic configuration 2s2, 2p4. Now, does this oxygen possess extra stability initially? No. But once you ionize, after ionization, you have taken away one electron, oxygen is expected to be not to be very happy, yes. But there is some trace of happiness. In what sense? Original O did not possess extra stability of half-filled p orbitals, but O plus indeed does have extra stability of half-filled p orbitals. So that is why taking away taking away electron from oxygen makes it slightly, more comfortable, more easy, because, okay, fine, electron is gone, but at least I have extra stability. In this case, nitrogen, it is worst. Not only have you taken electron away, you have also destroyed the extra stability. So that makes it more difficult for nitrogen. So it's a little more than expected, and that makes it somewhat easier for oxygen. So it is a little less than expected, and that is why O has a slightly lesser ionization energy than nitrogen. Can we compare O and F? Yes, we can. How shall we compare? Well, across the period, as we move from O to F, nuclear charge increases. Because of greater nuclear attraction, we find that more energy would be required for removal of electron. So ionization energy anyway is expected to increase from O to F. So that's quite okay. And that is the explanation why O is lesser than both N as well as F. How do you explain the fact that the first ionization enthalpy of sodium is lower than that of magnesium, but its second ionization energy is higher than that of magnesium? Okay. Now if I make Na to Na plus, this is IE1, and Mg to Mg plus electron, this is IE1 for magnesium. Now IE1 for magnesium is higher than IE1 of sodium. Yes, indeed. Why? See, although there is a pain, you're removing electrons, so which is not very nice. You're dropping electron away. That means you have to supply some energy called ionization energy, no doubt. But please note, sodium has a relief. After removal of electron, sodium gets a noble gas configuration. So after the removal of first electron, sodium attains noble gas configuration. So sodium lets this electron go relatively more easily. Magnesium does not gain any benefit of noble gas configuration, and not just that, sodium's nucleus has 11 protons while magnesium has 12. 12 protons attract the electrons more strongly in magnesium as compared to 11 protons in sodium. And because of these reasons, magnesium finds it difficult to let the electron go, and that is why it has higher first ionization energy as compared to sodium. This is explainable, fine. Now the second part. But its second I is higher than that of magnesium. Now let us see what happens when Na plus is going to Na2 plus. Na plus has a noble gas configuration, which is actually a very stable configuration. Now, the moment you want Na2 plus gas, you are trying to break noble gas configuration, which is really heartbreaking. It's a very difficult thing to do anyways. You cannot break away noble gas configuration very easily. So, IE2 of sodium is expected to be very, very high. And indeed, it is. On the other hand, if you have Mg plus, and you are taking away one more electrons, making Mg2 plus. Now, magnesium 2 plus, actually, it has attained noble gas configuration. This has noble gas configuration, which is very easy now. So, whenever any ion or atom attains noble gas configuration, it is more stable, right? So, when magnesium loses electrons to form Mg2 plus, there is some solace, some happiness that at least I have noble gas configuration, so it gives away electron relatively more easily. In this case, it is the worst. You are snatching away electron, which is bad, and not just that, you're also breaking noble gas configuration, which is doubly, triply bad. So that is why IE2 of sodium is way higher. IE2 of sodium is going to be much, much higher than IE2 of magnesium, because in one case, you are making the noble gas configuration, in the case of sodium, you are breaking the noble gas electronic configuration, which is very stable. What are the various factors due to which the ionization enthalpy of the main group elements tends to decrease down a group? If ionization energy is going to decrease down a group, well, that's very interesting. Why does it happen? The first and foremost factor is size. As we move down the group, more and more electronic shells are added to the atom. First point, right? when more and more shells are added, the distance between the nucleus and the electrons increases, right? And as the distance between the nucleus and the electrons increases by Coulomb's law of electrostatic forces, if the distance is more, attractive forces become less. And if attractive forces are less, it is easier to take the electron away against the attraction of nuclear charge, right? And that is why ionization energy is expected to decrease down the group, and it does decrease down the group, yes. Is there one more factor? Yeah. What is that? As we are moving down the group, more and more electrons are present between the outermost electron and the nucleus. Yes. These electrons in the intermediate shells, they also exert something which is called as the screening effect. They screen the outermost electron from the nucleus charge, or they repel that outermost electron, they try to push it away, and that also tends to make the removal of outermost electron somewhat easier, and that is the reason due to which ionization enthalpy of main group elements decrease. It decreases on moving down the group. The first ionization enthalpy values in kilojoules per mole of group 13 elements are tang, 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 tang. How would you explain this deviation from the general trend? Now, this is a very striking data and a very interesting graph. If you care to plot it, you would find boron is the highest, yes, with 801. And then you have aluminium, tarizami par, right? Gallium is very slightly, very slightly higher than aluminium. Just allow me to make a reference line so that, we can do it again properly. Gallium goes very slightly up, yeah. Barely 2 kilojoules per mole, but it's significant. And then indium further dips down. And then, shamelessly, thallium shoots up. It's a kind of ting tang, like this. There are two dips at aluminium and indium, or rather, it was anyway down the group, it was supposed to come down, so that's okay. Abnormalities actually lie when you talk about gallium and thallium. This gallium-thallium is a dangerous business, and the question is, why does this anomaly happen? Why is it that gallium and thallium, which would have been probably, you might have expected them to be somewhat like this, they just go up from their regular values? Why should we expect this? And how do we explain this deviation of gallium and thallium from the general trend? General trend is down the group it should decrease. It is decreasing for boron, aluminium and indium. Problem is with gallium and thallium. How do we explain this? The explanation lies in, the appearance of D block and F block for the first time. In case of thallium, it is what is called as lanthanoid, like a lanthanide contraction. Just look at their atomic number once. Boron has atomic number 5. Aluminium is 13. 5 plus 8, 13. So there is an increase in one shell. This is boron has 2 electronic shells, aluminium has 3. And atomic number goes up by 8, which is fine. From aluminium to gallium, gallium has atomic number 31. Only one extra shell is added. From aluminium to gallium, only one extra shell is added, but atomic number or nucleus charge increases by not 8 but 18. There is a sudden jump from 8 to 18. So nuclear charge increases substantially. Instead of 8, it has gone up by 18, out of which, you might say that if nuclear charge goes up by 18, we are also adding 18 more electrons. Yes, but out of those 18, 10 electrons are added to D subshells. And D subshells are not very good when it comes to protecting the nuclear charge or screening the nuclear charge from outermost electron. What does that mean? It means that the nucleus of gallium will now attract the outermost electron more strongly. Why? In spite of having one more shell, like aluminium has 3 shells, gallium would have 4 shells. Fine, one more extra shell added. But because nuclear pull is so strong, it has taken the electrons inwards. As a matter of fact, radius of gallium also is somewhat shorter than aluminium. It is closer to nucleus, it is attracted more strongly by the nucleus of gallium, and that is why ionization energy of gallium becomes somewhat higher as compared to that of aluminium. The same factor becomes much more pronounced in thallium. Why? Gallium to indium, this is 49, and now thallium is 81. Oh my God. There is a sudden jump from indium to thallium. Nuclear charges increases not by 18 but by 32. Wow. 32 extra electrons, protons are added to the nucleus. So 32 extra electrons are also there, but out of which 14 are added to 4f subshell. D electrons were not good at screening, right? F subshells are even poorer when it comes to screening the nuclear charge. That means they cannot keep the extra nuclear charge away from outermost electrons. Outermost electrons are now attracted more strongly towards nucleus in the case of thallium, and that is why the size of thallium also is not as high as it was expected to be. This feature is also attributed to a phenomenon called lanthanide contraction. After lanthanum in F block, you find all the lanthanides have continuously and very successively decreasing radii, because of which you find second and third transition series elements in D block have roughly similar radii after lanthanum. What I mean is, except group 3 and 4, if you take groups later on, 5 to 12, you find that second and third transition series have roughly the same radius. Why? Because nuclear charge has increased, but the extra electrons which have been added are not able to screen that extra nuclear charge. So you find a greater attraction of outermost electron by the nucleus, and that leads to an increase in ionization energy, because nuclear charge is now attracting outermost electrons more strongly. It is attracted more strongly, so ionization energy naturally increases. So these are the features. If I just summarize this in one sentence, you might say, what do we write down? What we write down is this: in case of gallium and thallium, nuclear charge increases by 18 and 32 respectively, right? The extra electrons are added to D and F subshells, which are not very effective in screening the nuclear charge against the increased number of protons. Because of greater nuclear pull on outermost electrons, the ionization energy increases. Which of the following pairs of elements would have a more negative electron gain enthalpy? Now, what is electron gain enthalpy? It is the energy released when an isolated gaseous atom accepts an electron to form an isolated gaseous ion. So naturally, it is the welcome energy. If you are accepting an electron out of happiness, atoms, they release certain amount of energy. Now, if you see O or F, you find oxygen has electronic configuration 2s2, 2p4. With electrons, it will give you 2s2, 2p5, which is beautiful, no doubt. But if you consider fluorine, which is 2s2, 2p5, if it accepts one electron, giving you 2s2, 2p6. Wow, this is a noble gas configuration. The moment noble gas configuration is attained, there is great happiness. And naturally, more the happiness, more is the energy released. So you find that fluorine is more exothermic, it is more negative as compared to oxygen when it comes to release of energy during electron gain. So electron gain enthalpy of fluorine is more negative as compared to oxygen and more exothermic. The second one, F or Cl. Now in both the cases, fluorine is 2p5 to 2p6. Chlorine is 3p5 to 3p6. So the happiness of noble gas configuration is there in both F as well as Cl. Then Can we compare FnCl? There is a very special case. What happens? What happens is this. Fluorine is a small atom. Agreed, it has 7 valence electrons, 2s to 2p5. And when one more comes, imagine a small room in which you have 7 people already, and somehow you try to push one more. They would tend to repel and they would tend to push the new person away because, although they might be happy, okay, fine, we have one more friend, but then, there's also some uneasiness because already there's not much room, right? So there are repulsive forces. On the other hand, if the same people had been in a bigger house or a bigger room, and if they get a new friend, they're happy. And the happiness is more explicit. Why? Because there's not much repulsion, right? They feel happier. So you find in case of FnCl, size becomes very important. Fluorine, nonetheless, both of them feel happy in attaining noble gas configuration. We are not opposing that. But then, as they attain the noble gas configuration, you have to appreciate that in case of fluorine, the size of atoms is much smaller. So, the incoming electron faces greater repulsion of remaining 7 electrons or the original 7 electrons, while in case of chlorine, because of bigger size, this repulsion is somewhat decreased. And because this repulsion is somewhat decreased, you find that, Cl is not as bad, in fact much better as compared to fluorine, and you find electron gain enthalpy of chlorine is more negative than fluorine. As a matter of fact, in this case, fluorine no longer gets the gold medal. The highest magnitude of electron enthalpy goes to, electron gain enthalpy goes to chlorine. Fluorine gets the silver medal, not the gold. It is second highest.